Hello, welcome to this video. Today, for a change, we're gonna do a physics problem. So here it is. We have a mass M dropped on this path from the height h relative to the ground, and this path is frictionless. And at the end here, we have a spring with a spring constant K, and below the spring we have a surface with friction with the friction constant mu, and it's the kinetic one. So the kinetic mu is just mu. And we're gonna solve two different questions here. First, after the mass being just dropped, how much is it going to compress this spring? And then the next question we're going to solve is, given that the mass comes back up and doesn't just stop on the friction surface, what is going to be the height? What is going to be the mass's height after it comes back? So let's begin. So the first question, the mass is dropped and we need to know how much it compresses. We're going to use it here. We're going to use conservation of energy, which says the delta, so the change of the total energy. So the potential energy plus the kinetic energy is the work that all the non-conservative forces are doing on our mass. So let's begin. First of all, we have to realize all the forces that are applied on the mass. So we first of all obviously have the gravitational force mg, and we have the normal force N, and at the bottom here we're going to have the force of the spring together with the force of friction. So down here is going to be the force of the spring together with the force of the friction. And this is going to be negative kx. And that's going to be down there. So now we need now to use this, we need to see how many of them or which ones are conservative. So we know that mg, the gravitational force, and the force of the spring are conservative, so we're not going to count them in this work formula. But the ones that aren't conservative are the normal force and the friction force. The normal force is always perpendicular to the direction of motion. You can see that because the direction of motion is always on this path, and the normal force is always perpendicular to the path. So it's always perpendicular to the direction of motion, which means that the work that the normal force does is zero. So we're just gonna ignore it. But that is, however, not the case for the friction force, because friction does do work, and so this is just the work of the force of friction. So now what is this? Well, friction, at least in this case, will always be opposite the direction of motion. When the mass is going to move here, the friction force is going to try to move it here. And the same goes, when the mass is going to come back, the friction force will try to pull it back. So we can say that, first of all, the formula for the work is the force itself dot the distance. So this is a dot product between two vectors. because the force and delta x are vectors with a size and a direction. So this is just the size of each one of them, the size of f times the size of delta x times cosine of the angle between them. Well, we just now discussed that they are always opposite each other. So they're always at an angle of 180 degrees. So this is cosine 180 degrees, which we can turn into just -1. So this is negative the size of f times the size of delta x. Now, we're gonna let x0 be the distance, say this distance, that m compresses the spring. And so delta x will be simply x0. x0 because that's just the distance that it traveled on the friction surface. Because the friction surface, I should say, is always below the spring, so it only applies when the mass is being compressed by the spring. It has a force on it from the spring. So delta x we can say is x0. And now, what is F, the friction force? Well, F is just the normal force times mu, or kinetic mu. And keep in mind, the mass is already moving when it enters here, so we're not going to think about static friction, because it's already moving. So N is going to be a bit hard to calculate on the entire path, because the friction is only at the bottom here, where it's perpendicular, where N is perpendicular to the ground. We can say that N is just mg, because M along here, along this path, does not move up or down. So we're going to have that this is N, which is mg, times mu. mg times mu. And that's times delta x, which we just said we're going to label as x0. So that is the change of the entire energy. Now we actually need to use this to calculate x0. So first of all, we need to realize that at the end, at the beginning, there is no kinetic energy at play. Because at the beginning, it's just dropped. It doesn't have any initial velocity. So here, kinetic energy, which is 1/2 mass times velocity squared, is 0. So let's write that down. At the beginning, EKI. And so the initial kinetic energy is 1/2 times mass times 0 squared, which is 0. And at the end, how much did the mass compress? Well, we know, the mass, when it fully compressed the spring, it got to a full stop. Otherwise, it would have kept compressing. Meaning that at the end, our speed is also 0. So the kinetic energy at the end is also 1/2 mass 0 squared, which is also 0. So kinetic energy doesn't play any role here in this formula, meaning that the only energy we need to think about is potential energy. So we're going to label at the bottom here y is equal to 0 to make things easier. And let's see. So from this we can say that the change in potential energy is still negative mg mu x0. So now, let's see. The potential energy at the end is the potential energy of the spring plus the potential energy of the gravitational force. The gravitational force, because as we labeled y is equal to 0, gravitational force does not, there is no potential energy from the gravitational force at the bottom, which is at the end of the motion. And so the only potential force at the bottom is the potential force of the spring, which is half k times x squared, where x is how much it was compressed. And so we can say that this is, at the end, it was half kx0 squared, and at the top, mg, and at the top there was no spring force, but there is potential energy of the mass of the gravitational force, which is mg, times, because this is h, this is y is equal to h, meaning that the potential energy at the top is mgh. So this is minus mgh, which is the potential energy in the beginning, before it started moving. So now you have this equation, and after moving here and doing the quadratic formula, you can find x0. Although I am not gonna do it because it's just a bit annoying and trivial of what you need to do here. So now let's go to the second problem, which is after the mass drops and the spring compresses and again releases the mass, to what height will the mass reach? What height will the mass reach? So let's erase the board and think about the second one. So let's, first of all, let me just write here the quadratic equation for x0, which is just tedious to solve. Well, it's not tedious, it's just the quadratic formula, and it's a bit annoying because the result isn't pretty. So that is the formula, that is how we can get x0. Now let's actually move on to finding what height will it reach after the spring releases it for the first time. Okay, now let's think about the second problem. We are given that the mass, after compressing the spring, it's released and it's not stopped by the force of friction here, and it does go up a certain distance. We'll call it L, and we need to find this distance, of course, in terms of m, g, k, u, and also g, the gravitational constant for. Shouldn't say that. It's confusing. So let's see. So we're gonna again use the formula for conservation of energy, which says, again, delta ET is the work that all the non-conservative forces are doing on the mass. So again, mg and the spring, negative kx, are all conservative forces, so we're not going to count it in this work formula. And is not a conservative force, but it's always perpendicular to the direction of motion, and so its work will always be 0, so we're also going to ignore it, and we're only left with the friction. And so this is again just F, which is the friction, dot delta x. And again, because friction is always opposite, at least in this case, it will be always opposite the direction of motion, we're going to have that this is negative the size of F multiplied by the size of x, of delta x. Now we need to think about what is delta x, because this time it's not x0. Because think about it, the mass dropped and then it traveled a certain distance x0 on the surface, but then when it got back to get to this height, it traveled another distance of x0. So in total, it traveled a distance of 2 times x0 on the surface with friction. And so delta x is actually 2x0. So this is negative 2x0 times the size of the friction force, which is again the normal force times mu, the friction constant, and n in this case again, because the friction is only applied here, n is only going to be mg. So this again multiplied by mg mu. So this is our change of energy, which is now how it's gonna help us solve it. Well, again, there is no, at the beginning and at the end, there is no kinetic energy at play, because again, I'm going to quickly go over this. The speed here is just dropped. The speed here is 0 at the beginning, and at the end, it's the maximal height it will reach, which we labeled L, which is again the point where it's going to stop, where it's going to stop on this path. So the velocity here and here is 0, so we shouldn't worry about any kinetic energy. So this is just the change in potential energy. Now this is only the change in potential energy from the end to the beginning. So this time we have no spring energy at play. We only have the potential energy of we only have the potential energy of gravity. So here it's y is equal to h, and because this distance is L, this is y is equal to L. Okay, so now from here we can say that but the potential energy at the end is mg times L, and the potential energy at the beginning is mg times h. Again, from the simple formula of potential energy of gravity. So this is the potential energy at the end, which is mgl, minus the potential energy at the beginning, which is mgh. And now we're going to have some fun, because now we get to cancel out mg. So this, and this cancel, and we get that L minus H is negative 2x0 mu. And so now L is very simply the initial height minus 2 times the distance that it will compress the spring, which we can find from this quadratic from this equation, which you can solve with the quadratic formula, which I won't do because it's just tedious and annoying. And so this is times x0 times the constant for the friction surface here, mu, which is how we get L. So this is L, and this is how we get x0, which is again very simple to do. It's just the quadratic formula. And that's it. Now, if you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems like this in the future. And finally, that's it.